Good morning to all and welcome to my course Engineering Thermodynamics. As of now, I have completed my theory part of concept of thermodynamics, definitions, some important terms, properties of substances, zeroth law of thermodynamics, temperature, thermometry, heat and work, their relations, first law of thermodynamics. In first law of thermodynamics, after that, we have find out the two or three properties, that is the internal energy U, enthalpy H, and specific heat C. Specific heat, we have the two types. One is the specific heat at the constant volume and specific heat at the constant pressure. This we have derived and we have find with the help of the first law of thermodynamics. In today's lecture, I am going to discuss about the few numericals related to the first law of thermodynamics, and this you know that it is depend on the properties of the about the first law of thermodynamics. In this, heat, internal energy and the work done is related. So this I am going to discuss today. So in this numerical problem number 1, it is related to the first law of thermodynamics, finding the state point, work and the heat. Numerical problem number 2, related to the first law of thermodynamics to find the heat transfer, means Q. And numerical problem number 3, related to the first law of thermodynamics to find the final pressure and the of the system. So this is the problem of related topic of first law of thermodynamics. A piston cylinder arrangement contains 1 kg of water. So mass is given as a 1 kg of water as shown in the figure below. The piston is spring loaded and initially rests on some stops. So here we will see that here this you can see as per the system is water and this is the your system and here is the water. The mass of water is given 1 kg. The piston is spring loaded. So here is a spring loaded. So it is a linear load is put and it is resting on these stops. These are the stops here. So it is pressing and it is resting on this stops. We should understand first the problem very carefully, then it will be easy to solve. If we are not able to understand the problem, it will be somewhat difficult to go ahead. A pressure of 300 kilopascal will just float the piston. So if the pressure is here inside this 300 pascal, that time it will be just float, means it will just leave the stop. And the volume of that time it will be 1.5 meter cube. A pressure of 500 kilopascal will balance the piston. So if you raise the again pressure from 300 to 500, then it will be balanced. The initial state of the water is 100 kilopascal, means without, when it is resting here, it is 100 kilopascal with a volume of 0.5 meter cube. So volume is given, P1, V1 is given. Heat is now added until the pressure of 400 kilopascal is reached. So we are giving some heat from here. Heat Q is given. So the next final stage is here, and here it is a 400 kilopascal. This 500 is not the final stage. It is a hypothetical state to solve, to make it easy for our problem. The final state is 400 kilopascal. That is our final and the initial state is fully two parameters are given, but the final state only one pressure is given. We have to find out the another parameter. So what we have to find out? Find the initial temperature and the final volume. So in this, what will be the volume here? V2 and the initial temperature T1. T1 and V2 we have to find out the first thing and find the work and the heat transfer. So del W and del Q we have to find out and also draw the PV diagram. Very interesting problem, and hope if you understand this thing, so many problem you can solve. And these are the answers. Initial temperature we will be getting 99.6 degrees centigrade. Final volume we will be getting 1 meter cube, that is the V2. Work done we will get 175 kilojoule, and heat transfer we will get 2435 kilojoule. So before we start any problem, first we have to sketch the system. So here I have drawn a sketch here. This is our cylinder. This is the piston. Here the water H2, and this is the system, and here Q is supplied. And here the volume will change. This is the point 1, this is the point 2, and this is the point 2 prime. And this 2 prime is given 500 kPa, 2 is given the 400 kPa, and as and when it is floating, it is given as a 300 kilopascal. So we have to see that mass, what are the given property? First, mass. Mass is given 1 kg. Now if you see the state 1, P1 is equal to 100 kilopascal and V1 is equal to 0.1 meter cube per kg. So suppose if it is not given small v1, total volume v1 is given, then we have to divide by mass. Here the mass is 1 kg, so it is not mattering. But if we have here 2 kg, then we have to divide by 2. So 0.5 by 2 it will be there. But here it is given a 1 kg, so v1 is equal to 0.3 meter cube per kg. So if you see here, it is a point 1, P1 and V1 is given. State point 1 is very much clear. So we have to find out by the table, by the steam table, given P1, V1, we will get the temperature T1 and we will get this is 99.6 degrees centigrade. So the first answer, if you see here, find the initial temperature. We got the initial temperature and initial temperature is 99.6 degree centigrade. And from the water table, we can get this 99.6 degree centigrade. Next thing, it is given as a hypothetical point 2 prime, and it is given that it is a 500 kilopascal and the V2 prime is 1.5 meter cube per kg. This is the actually a hypothetical case to give a direction of our work. Because here we have given the spring and spring constant is not given because F is equal to Kx. Neither X is given, neither the K is given. So we cannot find out this force by the spring. To have that thing, the final state, a hypothetical state given, this we will see in our next slide. When the heat is supplied to the system, the pressure will rise from 100 kilopascal to 300 kilopascal at constant volume. So here if you see in this, so up to initially it is 100 kilopascal, we can raise this up to 300 kilopascal and it is just touching this thing. So volume will remain constant. So from 100 to 300, the volume will remain constant. From 300 to 500, it will change 1.5. Initially it was 0.5. So this we can get it from here, that this you can see if we have to draw the PV diagram. So we have to find, got the P1 V1, we got the another point. I will draw here further, very much clear. So this is the point 1. From here this is the V and this is the P. So from P to V, volume is a constant, and this I am giving as a 1A point. From the 1A point, this is the 100, this is the 100 kilopascal, and this is the 300 kilopascal. And this volume is 0.5 meter cube per kg. From here to here, the condition is given. This is the 2 prime, and the volume of this 2 prime is given as a 1.5 meter cube per kg, and this pressure is given as a 500 kilopascal. This is given, but in fact this is not the real point. Our real point, the question is telling, it is a 400. So this is the 300 and this is the 500. In between exactly, this is the point 2. We are not concerned with this from here to here. This is only to find this problem. So from here we can see that, so this is the 400 is given, but how much it is? So we have to find out this V2. So by these linear relations we can find out that P2 minus P1A, P2 minus P1A divided by P2 prime by P1A divided by V2 minus V1A divided by V2 prime V1A. So V1A is equal to V1. So here, this you can see that P2 is equal to 400 minus 300 divided by P2 prime 500 minus 300 is equal to V2 minus V1A is equal to 0.5 divided by 1.5 minus 0.5. So 100 divided by 200 is equal to V2 minus 0.5 divided by 1. So V2 minus 0.05 is equal to 2. Because this. So V2, it is 1 by 2 or 0.5. So V2 is equal to 0. Here this is 0.5. 0.5 plus 0.5 is equal to 1 meter cube per kg. So we got this as a 1 meter cube per kg. So this is another answer which we want. So we got it. So now we have to find out the work done. And we have also find out the point, the real plot. It is from here to here and from here to here. This is our real position 2. We should not use up to here. This is the hypothetical point which is given here. So this we can see from here. So work done 1, 2 is equal to work 1 into 1A plus work 1A plus 2A. So just 1 to 1A, it is a constant volume process, and from 1A to 2 is a real process. So here we will get, this is constant volume, so this we will get the 0, and here we will get half P1A plus P2. So work done, we can find out from here that half P1A 300 plus 400 Then V2 is equal to 1 minus 0.5. So 3 plus 400, it is a P1 A 700 plus 350 into 0.5. So this we will get 750 joule. This is the work done, which we have got 175 kilojoule. Now we have to find out the heat transfer. So we know the heat transfer by the first law of thermodynamics, that Q12 is equal to U2 minus U1 plus work done. This U2 minus U1 is equal to, we can write small u1 U2 minus U1 plus work done. This M is equal to 1, and U2 and U1 we can find out for this and this from the steam table, and from there we can get this value, and here we will get the answer. The answer will be, as per this you can find out, and it is very simple, and this is you can get from the steam table, and put this value, put this work done, which we have got 175, and you will get the answer. So here I am not giving exact calculation. Here I am trying to give the abstract way so that you can do the work and you can find out the answer by your own. These answers may not be correct. I am not responsible for any answers and all. Please try to do yourself and get the answer. Now I will go for the next problem, that is the numerical problem number 2. Here, consider the system shown in the figure below. Tank A has a volume of 100 liters and contains saturated vapor R134A at 30 degrees centigrade. When the valve is cracked open, R134A flows slowly into the cylinder B. The piston mass requires a pressure of 300 kilopascal in cylinder B to raise the piston. The process ends when the pressure in tank A has fallen to 300 kilopascal. During this process, heat is exchanged with the surrounding such that the R134A always remains at 30 degrees centigrade. Calculate the heat transfer for this process. So here we have a tank here. In tank we have R134 is filled. The gravity direction is towards this. There is a cylinder, there is a piston, and the cylinder. And when the valve is cracked open, the piston mass requires a pressure of 300 kilopascals in cylinder B to raise the piston. So to raise this piston, we need a 300 kilopascal, then only it will be able to raise. The process ends when the pressure in both the side, here and here, it is 300 kilopascal. It means at 300 kilopascal, your system is in equilibrium. Both systems are in equilibrium. So in this, there is a heat exchange and the temperature is remained constant in this. So we have to calculate the heat transfer in this process. So we have to see Q. How much is the Q? So here, first thing, what is the system here? That we have to discuss. And the answer is 84.61 kilojoule, that I will be discussing. So here, what is the system here? Tank A or the tank B? So this you can see here. If I give the argument that tank A is a system, then once I open this valve, the refrigerant will go from here to here. Then mass will not be remain constant. So we cannot take A as a constant. Tank A is a constant. If we take individually this tank B, if the tank B is raising, the volume of the mass is increasing. So this cylinder B is also not a system. So what is the system? The actual system will be from here, total A plus B. So the A is not the system, B is not the system, A plus B is the system. So first we have to decide what is the system. System means the mass should remain constant. That zone is called the control mass system. We are discussing here all this first law of thermodynamics with respect to the control mass system. So that we have to. So here the system is A plus B, and here the name of the substance is R134A, which is a refrigerant. So here first we have to see the state point. So state point V1 is Vg at 30 degrees centigrade because it is given the saturation. So from the table we will find out the specific volume at 30 degrees centigrade. So if you get this specific volume, this mass is equal to Va by V or V1 by V. V1 is given as a 100 liter. So this is 100 into 10 to the power minus 3 meter cube. From here, we can also get the internal energy U1 from the steam table for the Vg at 30 degree centigrade. The state 2 is given. P2 is equal to P lift is equal to 300 kilopascal. When we increase the 300 pressure by putting the heat, the piston start lifting. First lift will happen whenever the system is 300 kilopascal, and in the condition it is given that at 300 kilopascal both the tanks are in equilibrium. After that it will not move. So this is the equilibrium condition. So P2 is equal to P lift 300 kilopascal, T2 is equal to 30 degrees centigrade. Both are given. So state 3, state 2, V2 and U2 we can get from the table, because if you know the two state postulates, we can get remaining thing by the help of the steam table or the refrigerant table. We can get V2 and the U2 directly, we can read from there. Now we have to find out the work done. We know the work done is equal to PdV. For the simple incompressible substances, the work done is equal to PdV. So here P is a P lift. It is given 300 kilopascal. V2 and the V1 we have got from here. If you see, V2 we got here, V1 we got from here. So we got everything. So work done. Mass is also given. So P lift into mass V2 minus V1. We will get the work done from here. And heat transfer, we can get from here that heat transfer is equal to M U2 minus U1 plus work done 1 to 2. And this will come 84.61 kilojoule. So in this way, because work done we have got from here, we will put this value. U2 we have got, U1 we got M. All the value we will get from steam table. Steam table or the refrigerant table. Here we have R114A. So from there we can get it, and if we put this value, we will get the value of heat transfer. We will get the value of work done. So these all things we can find out, and we have got the answer as per the 84.61 kilojoule. Now I will discuss the numerical problem number 3. A very simple and very, you can use direct method, but here I am using the first law of thermodynamics. So we will discuss in respect of the first law of thermodynamics. So a water filled reactor with a volume of 1 meter cube is at 20 megapascal. It is very high temperature, very high pressure and a very high temperature, and is placed inside a containment room of 100 meter cube as shown in the figure. The room is well insulated and initially evacuated. So room is well ventilated, insulated, and it is evacuated, means there is no friction, means if expansions are taking place, evacuated means it is vacuum, so work done is zero. From here you can identify. And insulated means heat transfer is also zero from the room. Due to failure, the reactor ruptures and the water fills the containment room. Find the final pressure. So we have to find out the pressure by the help of, so this is the diagram. This is the room here. This is the reactor. Here we have the 20 megapascal and 1 meter cube. This is the V1 and the P1. Room temperature, this room volume is VR is equal to 100 meter cube, and this is given 360 degrees centigrade temperature. These things are given, so we have to find out the final pressure. So what is the P2 here at the room? That we have to, this is our question. Answer is 568.515 kilopascal, and that we will see how we are going to get this answer. So we will see that. Let's draw the schematic of the problem given. So here we have this, room. This is the reactor, and this is the insulated here, and this is the vacuum. So here V room is given 100 meter cube. This volume is given 100. So state 1, first we have to find out the state 1. State 1 is given pressure at 1. This is the 1 and this is the 2. P1 is given 20 megapascal. P1 is given 360 degrees centigrade. So identify the state 1 from the property table. We will get V1 is equal to M V1 by V1, and here it is V1 is given 1 meter cube, and V1 we will get from here, small V1 we will get from the table. From here we can find out the mass. We can get the mass of the system by the state 1. State 1 is only given to find out how much mass is there. Now we have to find out the state 2. Only one point is given. Then first use the first law of the thermodynamics. So for the state 2, only the one parameter is given. So in this, we know that state 2 is equal to V2 is equal to V room by M. So M we got from here, M we got from here. V1, the room is, V1 is, V room is given 100 meter cube. So we can get the V2. So by the first law of thermodynamics, we got now V2. So Q12 is equal to M U2 minus U1 plus W12. So here it is a vacuum. So this W12 is equal to 0. This is 0. And it is insulated. So del Q is equal to also 0. So here we got M U2 minus U1. So here M U2 minus U1 is equal to 0, or U2 is equal to U1. So if you put this value U2 is equal to U1, then you will see that we got now V2 and the U2. V2 we got from here, U2 we will get from the steam table, we got the state 2. So if you got this state 2 by the help of V2 and the U2 from the table of steam, we can read pressure P2, and this P2 we will get 568.75 kilopascal, and this is our answer. It is directly you can measure by using this thing. Please do yourself, then only you will be able to do. I cannot show here your steam table also, so try to understand, try to follow the system of how this all I am showing you as abstract. I am trying to give you the concept how to find out the different values, but you have to do by your pen and you use your calculator to find out the real result. All results, your answers may not be exactly correct. Try to find out the correct answer and then you use the table and then you find out the answer. So these are the references I have used. Eunice Sengel, Michael A. Bowles, Thermodynamics and Engineering Approach, Tata McGraw-Hills. Then http www.youtube.com. This is also from Professor Suman Chakravarti, IIT Kharagpur, India. Any questions you are welcome to ask. My email is ydwivedi@gmail.com. You are always welcome. I will feel very happy if you like it, subscribe it, and comment if you want anything. Thank you very much for the joining. We will see our next class, some few more numericals, and then we will go for the second law of thermodynamics. We will discuss the second law of thermodynamics with the next class. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.